have that with quiz, so I was like, oh, whoops. Oh, okay. Oh yeah, there's your chapter 5. And then you're missing your name on this one. So at least put a first name.
No name on?
Yeah. Is it you?
No.
Yeah.
I don't think so.
I was trying to like do handwriting analysis, but it didn't work out too well. Second look.
I don't think it is.
All right, let's go ahead and get started. So I have a ton of papers to keep giving back to you. So I'll probably hand them out while you take your quiz and all that. And so at this point, I think I caught up on grading. The only thing I did not do yet is the energy lab. So what, as of 11/14, Energy lab not graded. But everything else you handed to me should be graded. So homeworks, labs, everything. So double check your grades, make sure everything looks good. I have one homeless, chapter 5 homework, I think it is. Someone who like wrote in black pen. So if it's yours, let me know. And so again, just check your grades, make sure everything's accurate. And if anything is wrong, let me know ASAP. And then, of course, don't forget to register. Many of you have already sent me emails, and so just keep doing that. And I still need to make your extra credit column, but it is coming. And then just another reminder that we have the extra credit speaker. And her name is Carly, I believe. And this will be December 2nd at 1 p.m., tentatively HEC 112. And she'll give a talk about her research, and then you can probably ask her questions. It'll be over Zoom, but you can still ask her questions, you know, how do you get to grad school, anything that you want to know, or, you know, why did you pick your field, anything. All right, any questions before we get started?
You said you can watch that online, because I work Fridays, so.
Yeah. Yeah, I'll post the recording like I've been doing with all this stuff, and so you'll be able to watch it online and just send me an email like, I like this about the talk, and that'll count for your extra credit. And so just to put us kind of where we are, this is our last week of lab. So this last week it should be a pretty fun lab. It's a titration lab. And then next week will be the lab final. And so yours is not quite written. It will be based off of my 200 level final, but there'll be like some matching, you know, what's the equipment, what do you do with it type of thing, can you name the equipment, and then I'll have some like sample calculations like you've done in class, or identifying what flame color something is, that type of thing. So it shouldn't be a surprise or difficult. Other questions?
And is the final, is that on Monday or Wednesday in that last week?
Oh, that'll be on Wednesday during your lab time.
And that's for the lab final or the final final?
The lab final.
Okay.
And then the final will be on the Wednesday as well of week 11. So the week after this, but not during lab time. And we'll do a review on Monday like we did with the midterm. And I'll do it like the same thing, you know, same style of questions so you can get a good feel for what's going to be on the exam. All right, so let's start chapter 8. So that's solution concentration and solution stoichiometry. And we've kind of touched on this as we've been in lab, and of course, like you work with chemicals and they have molarity and concentration. And so now we're just kind of putting it all together. And if you remember back to a couple of labs ago, I think you had like the light bulb mixtures where you tested the salt, regular plain water, and then salt water. And so just to remind ourselves, so we know we can mix table salt with water, and it looks like it disappears or something, and it makes our homogeneous mixture, so we remember our term homogeneous, meaning the same throughout. And of course we know the salt is still there. You can taste the salt water, and it's salty. Then we mentioned purification techniques, so we could do a distillation, boil it, away the water, and we're left back with our pure water. And so we mentioned homogeneous mixtures are called solutions. And so the minor component of a solution is called the solute. That's usually your solid that you're dissolving. And then the major component is called the solvent. So in our case, we're usually looking at aqueous solutions. And so anytime we see aqueous, we know that's going to be water-based. But, if you're doing like an organic chemistry reaction, you could have any of the solvents, benzene, ether, dichloromethane, et cetera, et cetera. You go on and on, ethanol. And so now we're going to look at a classification of mixtures. So we have this thing called a colloidal mixture. And so all this is when the particles are large enough to scatter light, and such as like nanoparticles, but larger. And this gives a phenomenon called the Tyndall effect. And so this makes colloidal mixtures appear cloudy or opaque. And so this is just a colloidal dispersion of gold in water. And so you're probably familiar with some sort of colloidal mixture and you don't even know it. And so we can see this Tyndall effect with the fog or mist. So you get like the weird scattering of light. So it's kind of hard to see, like if you have a headlight in the fog, where is it actually coming from, how far away? So that's all the Tyndall effect. And so that's just formerly a gas-liquid medium. So your liquid aerosols. I don't know if anyone was up early this morning and saw that nice freezing fog. Yeah, so that would kind of give you the Tyndall effect. And so other aerosols would be like dust and smoke. So again, a gas-solid mixture. But then other things are also considered colloidal mixtures, like your whipped cream, shaving cream, and then even like mayonnaise. So that's a colloidal mixture. We mentioned gold, so then other colloidal mixtures could be other pigments, ink, blood, clay. All that's a colloidal mixture. Pumice stone, so that's going to be a solid gas mixture, so you have the holes left from the gas in your pumice stone. Same with styrofoam. And then cheese is also a colloidal mixture. And then your gemstones would also be considered colloidal mixtures. So what tends to give the color of your gemstones is some sort of impurity. And so that's going to be your solid-solid mixture. So ruby glass is one, and other gemstones. So comparing back, now again we're thinking of our salt versus a sugar mixture. So why do things dissolve? And so we have this, you may have heard of this, like dissolves like. But now we really can understand what that means. So we went over our attractive forces, right? Our hydrogen bonding, our dipole-dipole. And so if something has hydrogen bonding, two things is hydrogen bonding, that tends to be really soluble. And so what you're comparing to with these solubility is there are attractive forces holding the solute particles together. So you have your solute, right, your solid sodium chloride or whatever ionic compound you're looking at. And so they're held together by some sort of electrostatic charge. But then there's also going to be attractive forces between the solvent molecules. And so again, now we're trying to think of sodium chloride on really the molecular level. And so this is kind of before it's dissociated. You can just imagine a crystal of sodium chloride here, and then your water comes along. And so what happens is if the attractions between the solute and the solvent, so in this case, right, my sodium and my water, or my chloride and my water, if those are strong enough, then that means that it will dissolve, and in this case, it's overcoming these solute-solute interactions. So overcoming those attractive forces between the sodium and the chloride. And then, so we know, again, it tends to disassociate, and like we've mentioned before, our partial negative region of oxygen is, of course, oriented towards our sodium, and then the chlorides hang around towards our partial positive region of hydrogens. And so again, those attractive forces and so we looked at water, This is what makes water extremely awesome, to say the least. And so like we mentioned, there's an uneven distribution of electrons within the water molecule, and so that causes the oxygen side of the molecule to have a partial negative charge, and our hydrogen to have partial positive. And so like we saw, those were strong solvent-solute interactions, and it dissolved the sodium chloride. And so there it is, our big crystal then of sodium chloride. So it would start attacking kind of the outer layers, dissolving it, and nucleating it. And then, of course, it surrounds it, insulating it from other ions. And so like you saw in lab, materials then that can dissolve in water and form a solution that will conduct electricity are called electrolytes. So again, our ions dissociate, so I'm just going to write there ionic compound. But then if we were to do sugar, do the same experiment with sugar, well, sugar is not an electrolyte. And so these tend to be, again, your compounds or your molecules. So they're one big discrete unit. So you put them in water, it may hydrogen bond, but it's not going to disassociate, and so it dissolves. But what do you know about sugar compared to salt and trying to dissolve it? Yeah, Michaela. Or you're like losing electrolytes, do they say? Yeah, it's with that, it's just you have to have ions in your blood to transfer, like the same thing. You need something to do an electrical current. So everything in your body is all electrical currents, right? Moving your muscles, your heartbeat obviously is really dependent on the right levels of magnesium and potassium. And so yeah, that's all they mean by that, is replace those electrolytes that you sweat out. So they're going to come out with your sweat. So your sweat, of course, is salty, so all those electrolytes are coming out, and then you want to replace them. And then I don't remember if it was in this lab class or my other lab class, but someone had asked, and this is slightly an aside, about distilled water and drinking distilled water. And so you probably wouldn't want to drink distilled water. It wouldn't hurt you, but over time, if you're drinking some sort of water that's ion depleted, that's going to be essentially leaching those ions from your body as well. And so that wouldn't be good for you in the long run. You might start to have, cramping issues you'd notice, just if you're not getting those electrolytes. So you have cramping usually from lack of potassium or magnesium ions. And so that would not be a good long-term plan. But you could drink it, just, taste it, but do not change your diet to distilled water without ions. And so what do you remember about sugar versus salt if you try to dissolve like the same amount of sugar versus salt? Yeah, so if you have to warm up sugar to get it to dissolve, that probably means it's not too soluble or doesn't want to go in that readily. And so you probably know, like at coffee shops, that's why they have that simple syrup prepared already of the liquid sugar. So it is solubilized, and they made a supersaturated solution. So that's essentially explains it. Is it takes a little bit longer to dissolve since it's not disassociating. And so it has to work probably a little bit harder to overcome those solute-solute interactions. And so if we take a closer look at the sugar-water issue, so there's still some, let's get another, because sugar, that is not, I guess that works. It's a little cartoony, but what I'm trying to emphasize is sugar does have some OH groups on there. So there's our oxygen bonded to hydrogen, another oxygen bonded to hydrogen. And so with those, it has some hydrogen bonding then. So this, what's going on here is all H bonding interactions, so hydrogen bonding. And so we think back to that like dissolved like. They both have hydrogen bonds in them. So then you can start getting those solute-solvent interactions, and then it dissolves the sugar. And so from this depiction, you would have, again, your hydrogen bonding. So you notice the water molecules are kind of oriented near those OH groups on the sugar molecule as well. So then, again, what is an electrolyte? And so let's look at how we can classify them. So we have strong electrolytes, and these are things that completely disassociate into ions. And so usually they're going to be soluble on your solubility rules. And did I hand out solubility rules in this class or no? Okay, so it looks like I did. If you need another copy, I have some more at the front. So feel free to grab it, or it's slightly different than the one I gave you, so whichever one you find easier to read. And so one example is calcium chloride. So that, if you look at the solubility rules, is going to be soluble. So ions of chlorine tend to be soluble, and so we know it's going to completely disassociate. And so other examples of electrolytes, and we're going to cover this next chapter as well, are going to be strong acids. And so I'll let people get the sheets. So a strong or a weak acid isn't defined by how dangerous it is, but rather whether it fully disassociates or not. So your strong acids are going to be HCl, nitric, nitric fully disassociates. The first disassociation for sulfuric is strong. And let's see, phosphoric. Again, the first disassociation is strong. And let's see, I'll add on there. So hydrobromic and chloric acids are the ones missing from this list. Oops, I misspelled chloric. And HI. All right, so this is kind of some of your common strong acids. Again, we'll revisit this next chapter, but all this is saying, if it's a strong acid, it completely disassociates. Same thing with your electrolytes. So we can, go crazy with examples. And again, you're just basing it off of those solubility rules. So if it says it's soluble, that means it's going to completely disassociate. And then, of course, like we've seen, again, our molecular compounds that dissolve in water do not form ions. So molecular compounds cannot form ions. Just remember that. Your covalent compounds, I'll put their covalent too. So it's only ionic. And then, so our weak electrolytes are anything that partially disassociates. And so this is kind of beyond our scope, but looking at kind of these insoluble compounds. So if you were to continue on in like the 200 level series and stick around till spring or winter quarter, you would look into the yeah, there's a little bit of those insoluble compounds that is in solution. How do you quantify that? All that sort of thing. But we're not there. We're just going to accept, okay, when it means insoluble, that pretty much means, not a lot of it is going in. But as you can imagine, right, some of it is going to be soluble. And again, you can always refer back to Wikipedia to give you an actual number of, well, how much can dissolve. And so I'll just pull up again, like silver chloride. If you look on your rule sheet, it says chloride salts are all soluble except for a few exceptions, and silver is one of them. And where is the solubility? And so again, really small solubility, 520 micrograms in 100 grams of water at 50 degrees Celsius. So again, that's just giving you a taste, yeah.
So when they're asking about is something soluble or not, and it has one part that's soluble on the list and then one part that's not, does that mean it's not?
Yeah, correct.
Okay.
Yeah,
So it always takes the precedent of the one that's not.
yeah.
Okay.
And then again, that's just like your general rules. And if you see like weird discrepancies, it's just because of the solubility that some of it can go in. And so some rule sheets have like slightly different things on them. And then so with our weak electrolytes, the other thing that would be a weak electrolyte would be weak acids, which again, we'll talk more about in depth next week. But this is formate shown here, but vinegar or acetic acid, right, HC2H3O2 for acetic acid, that is a weak acid, and you would use these half equilibrium arrows to show that. And so all this is saying is in solution, the acetate ion can pick up an H plus and reform acetic acid. So same with HF. So HF, extremely dangerous to work with, so you wouldn't want to get it on you because it'll dissolve your bones. And then the problem with that is it liberates like calcium in your bloodstream, which will then re-solidify somewhere. And of course, wherever it re-solidifies depends on how severe your medical emergency is. But if you ever get HF on you, to even work with HF, you have to have a calcium cure like on hand so that if you were to be exposed, then you just put that calcium treatment on you so that the HF goes for that and not your bones. Again, HF considered weak just because that fluorine can pick up our hydrogen ion in solution and reform HF. And so again, we've seen, so if we were doing the light bulb test, so sodium chloride would light up our light bulb really strong. Hydrochloric acid would light up your light bulb really strongly. Acetic acid, again, we mentioned that was a weak acid since it's partially disassociated, and so its light bulb would be just a little bit dimmer. And then so sugar would not light up a light bulb, and so it's a non-electrolyte solution, so no light from our light bulb. And so there's just another picture, so non-electrolyte versus our vinegar versus our sodium chloride. And so we've kind of danced around this, seen this in lab. So what drove those precipitation reactions? And so we're finding not all ionic compounds dissolve in water. And so we looked at silver chloride, I believe, in lab. And if you either make it with a reaction, of course, that's a precipitate that's coming out, or if you were to just try to add silver chloride to water, it mainly remains as a solid and just looks like a white powder. And again, we mentioned that only 520 micrograms can get in there. And so in general, a compound is termed soluble if it dissolves in water and insoluble if it does not. And so we've seen this in lab. So for example, silver nitrate does dissolve. So you would look at your solubility rules, look at your nitrates, and I don't think there's any exceptions to insoluble nitrates. Well, I'm sure there are for odd compounds, but not for like common ones. And then again, silver chloride, if we take this, react it with sodium chloride, they do a double displacement, then that gives us our silver chloride, and it comes out of solution. And so you probably already are getting a sense of this, that whether a particular compound is soluble or insoluble depends on several factors. So it depends, right, again, on that like dissolves like. Do they have the same similar like hydrogen bonding and hydrogen bonding versus like nonpolar, nonpolar, so those tend to dissolve. And so it's not easy to predict whether a compound will dissolve, so you have to do it experimentally. And again, that's what the Wikipedia data is kind of showing you. Somebody did this, then they quantified it, they actually had to measure how much. And so that's where we get these solubility rules from. So I think today's chart kind of looks more like this chart, which is my favorite version of the rules. I don't know why, I just think it looks more concise and easy to read. And so the top half of the chart is all your soluble compounds. So notice, especially your group 1, they tend to be soluble. Ammonium salts tend to be always soluble. Same with nitrate, acetate, so they don't tend to have exceptions. And then these ones have exceptions, so chloride, bromide, iodide. Notice that silver, mercury, and lead, so those are all heavy metals, and their compounds tend to be insoluble. Sulfate, so that has more exceptions, so more of your alkali earth metals tend to be insoluble. And then the bottom half are generally insoluble. So notice your hydroxides, your sulfides tend to be insoluble, again, unless they're pairing with your group 1 or your group 2. And then you have these, the slightly solubles, which can always cause issues in word problems or exams, but that's, again, where slight discrepancies might arise in different rules. And then carbonates, phosphates, those all tend to be insoluble unless they're with group 1 or ammonium. All right, so let's do a little practice, see if we can determine, are these soluble, insoluble? So I'll scroll back up. And again, grab a rule sheet if you need another one. And I'll give everyone a couple of minutes to read and determine which one of those are likely soluble or insoluble. So what did we get for A? This was lead 2 chloride. So soluble, insoluble. So I see a lot of shaking the head. So insoluble. So good. So that was one of our exceptions for chloride. And so I pulled up a Wikipedia page to put things in some context. So that's only 0.99 grams can go into 100 mils of water. What about copper chloride? Or copper 2 chloride. Soluble, insoluble. So let's see. So chloride, it's not under our exception though. And it's copper, so I don't see copper. So do we think it's soluble, insoluble? So then, yeah, so it should be soluble. And so we look at Wikipedia. So they have 70.6 grams in 100 milliliters. So that, yeah, that seems pretty soluble. That's a lot. And then C, calcium nitrate, soluble, insoluble. I see a thumbs up, some nods. And so nitrates, again, almost always soluble, so that's going to be soluble. And this one kind of amazed me with how soluble it is. So it has several different forms. So the anhydrous, you can get 1,212 grams in a liter, so that's really good. And then it has the tetrahydrate forms, and you can just compare. And of course, increasing solubility with increasing temperature. And then the last one, barium sulfate. What do we think? So here, insoluble, and so, yep, so sulfates, and then, oh, it's one of our exceptions. So it's going to be insoluble. And looking at that one, so that one is only 0.2448 milligrams in 100 milliliters, so that is pretty insoluble.
On the copper chloride one, I'm a little bit confused because on the left side it says chloride is soluble, but then it says exception is copper.
Is that on the sheet? Oh, that's funny. That's annoying. Oh, but it's copper 1+ on the sheet, yeah.
Okay.
Yeah, so the sheet had copper 1+. But yeah, that's why it's always confusing with these rules too.
You have to pay attention to what the charge is.
Yeah, because the charge will dictate to, right, the solute-solute interactions.
Also the polarity of it.
Yeah, or like because the ions, basically like the more charged it is, the stronger those attractions are, at least presumably, but then it also depends on ion size, so there's a lot of factors, hence why it's hard to predict. All right, feel good about those? And so looking at the temperature dependence of solubility of solids, and you probably know this, and in general, the solubility of the solid increases as the temperature increases, and so that makes sense, right? More molecular motion means that probably something's more readily dissolved, and so there are some exceptions, and so they put the notable exception on there, cerium sulfate. So not entirely sure why, but maybe with the increasing temperature, it disrupts these solute-solvent interactions, and so it doesn't solubilize as readily. But that's kind of interesting. But everything else, again, increases solubility with increasing temperature. And so gases are the opposite of solids. So maybe write that. So gases, opposites of solids. So we just finished saying that if we increase the temperature for solids, we increase solubility. Now gases do the opposite. And so, of course, gases have a low solubility anyways, since they are generally nonpolar molecules. So we've looked at that, right? The gases tend to just be nonpolar with those London dispersion forces. And so gases that do have a high solubility are maybe reacting with water. And CO2 is also kind of part of that. So CO2 makes carbonic acid. Well, first it makes this, then that makes carbonic acid. And so for all gases, the solubility of the gas decreases as the temperature increases. And so that makes sense. So if you are increasing the temperature, then the gas just tends to escape. And so you can see this in this cold versus warm soda. So if you really want to get that fizziness, and you have that warm soda, you can pour it over ice so you still get the fizziness, but less carbon dioxide dissolved, so that's why it's bubbling out, versus the cold soda, so you have more carbon dioxide dissolved in there, and so less bubbling. And so the delta H for this is also exothermic, since we do not need to overcome those solute-solute interactions. So again, we mentioned our gases are very loosely bound to each other with their London dispersion, so they just tend to, again, float out. And so how can we make a solvent hold more solute then? So we can vary the temperature, or in the case of our gases, vary the pressure. And so you kind of saw this with your sodium acetate, although I'm not sure it worked as well as we would have liked it to. But you saw how you could take your sodium acetate, dissolve it, make your supersaturated solution, and then cool it back down, and you got those crystals forming again. So same thing if you made, have you ever made like rock candy with the sugar? Yeah, so I see some nods. So same thing, you make a really supersaturated sugar solution, then you provide a string or a wooden stick or something, and that allows for nucleation. So then your crystals start forming on there, and then you get your nice rock candy. And so sometimes these solutes, you don't get the crystallization, and you have that supersaturated solution. So that was kind of what you were seeing with the sodium acetate, because it would be a liquid, not doing anything. And then if you kind of poured it out or moved it, then all of a sudden it might crystallize. And so supersaturated solutions are unstable, and it can lose all the solute above saturation when disturbed. So again, you saw that with the sodium acetate, but then shaking a carbonated beverage does the same thing. So you shake it, and then now all of it comes out of solution. And so this is how they would pack your soda or whatever beverage. And so we have this pressure dependence of solubility of gases in water. And so all this is your solubility of a gas is dependent upon this constant times the pressure. And so again, this is one of those scenarios where you just kind of have to watch the gas constant, watch what's provided. So each gas has its own constant. And so in this case, if you're looking the KH for CO2 at 25 degrees Celsius is 3.4 times 10 to the negative 2 molarity per ATM. And so molarity we'll get to is just a concentration. And then so per pressure. And so again, we're seeing dimensional analysis how that will work. So that's your KH times it by your pressure. So your pressure will be an ATM. then those ATMs will cancel out and give you something in molarity. And so at the soda factory, that's what they do. They can the CO2 under pressure so they can get the desired solubility of the gas and then seal it up. And so then it's all dissolved in solution until you, of course, pop that tab open and the CO2, or if you're drinking something fancy like nitrogen, your nitrogen beverage will be released. Like those nitro beers now. All right, so now we're getting into more the nitty gritty, or at least we'll start to get into the math, really. And so to make a solution, and this is what our lovely stockroom does a lot of the time, right? They have to make a certain solution for us depending on the lab manual. So how do they do that? So they start with some sort of stock solution, and so we have these terms, so dilute and concentrated. So the stockroom buys a nice concentrated solution. So concentrated would generally be like 12 molar, anyway, wear down to like 6 or so. And so like all your acids, for example, they come in 12 molar, so super concentrated. And then dilute is probably anything 3 molar or less, roughly. And then, so then we just want to quantify it. So again, the stockroom has to have some sort of unit. What are we going to make? What's the concentration? And that's just amount of solute in any given solution. So this is kind of like your overview cheat sheet of all these solubility terms, and then we'll go over them individually more. So molarity, this is the standard one. So again, you've probably seen it all the time already in lab with the little bottles. And so that's just moles over liter. And so that's not to be confused with molality. And so sometimes molality is used and sometimes it's more appropriate. And that's just going to be moles per kilogram then. So the mass of your solvent. Then we'll look at mole fraction. So that's just your amount of solute in moles over total moles. Mole percent, so you can convert your fraction to percent. Then parts by mass and percent by mass. And then we'll look at parts per million, parts per billion, easy tricks for that, and whatever part by volume. So to prepare a solution, we have to know the amount of solution and the concentration. So for one example, we need 500 milliliters of 5 grams in 100 milliliters of solution. And then of course we'll calculate the mass, dissolve that, start with our amount of solution, and then have our conversion factor. So we have a 5% by mass weight, so that's going to be 5 grams dissolved in 100 grams of solution. So that's weight by weight. And then, so how you properly prepare a solution is, so you have these volumetric flasks, and they are specifically made for measuring 1 unit of volume. So in this case, this would be a 1 liter volumetric flask. And so you start out, so they want to make a 1 molar sodium chloride solution. So the first thing you would do, you would calculate how much 1 mole of sodium chloride weighs. So 58.44 grams. Then you pour that into your volumetric. Make sure you get that all in there. Use a funnel. Then you add water. You'd be kind of pouring down the sides to make sure that no sodium chloride is kind of stuck above here. And then you get it to around here or so, just enough so it's dissolved. And then you want to shake it, make sure it's all homogeneous. And then at the very end, you top it off and bring it exactly to the 1 liter line. Now, if you go over, you have to start all over. So once you go past that point, now it's inaccurate, your volume's all wrong, so you would have to begin again. All right, so let's look at molarity. So again, molarity, this is the one we see all the time. It's used a lot in your calculations, especially stoichiometry. And so this is moles of solute per 1 liter of solution. So again, molarity is just moles over liter. And so it describes how many molecules or atoms of solute are in each liter. So if we have a sugar solution that's 2.0 molar, then we know that that 1 liter of that solution contains 2 moles of sugar. And so this is where proportions tend to work out well. So then you know that 2 liters is 4 moles of sugar, or half a liter is 1 mole of sugar. And don't forget your triangle trick to help you with the math. So moles, molarity, liters. And so again, don't confuse molarity with molality. So molality, those L's. And then it's a little m, so lowercase m. So that's the distinction between the two. And so molality is defined as moles of solute per kilogram of solvent. And so the advantage to molality is that it does not vary with temperature, since it's based on masses, not volumes. So sometimes it's considered more accurate. And then, so parts. So the parts, you kind of have to read to what it's saying. So parts are generally measured in the same unit. So you'll see it grams per gram, pounds per pound, etc., or by volume. So milliliter per milliliter, liters per liter, gallon per gallon. And so usually it's a percentage. And so if it's a percentage, then it's just parts of solute in every 100 parts of solution. So that means if it's 0.9% by mass, so then just kind of assume 100 to help you. So if we have 100 grams, it's 0.9% by mass, then we have 0.9 grams of our solute in every 100 grams.
When it's at a percentage like that, it's always gonna be that over 100.
Yeah. And then, so the parts per million, let's look at that more specifically. So the parts per million, now that's going to be 1 part per a million. And personally, I think that's a little confusing for me. And so I prefer this calculation. So a part per million is also equivalent to a milligram in either liter, or I like to say a kilogram of solution. So milligram per kilogram. And you can see that 10 to the 6 factors. So milligram is 10 to the negative 3, kilogram 10 to the 3rd. So that gives you that 10 to the 6 difference. So there's your million factor. So if you were doing a part per million, I'd probably convert your solute to milligrams and your solvent to kilograms to help you. And so that means a part per billion then, I like to think of it as how many micrograms are in a kilogram. And so of course a billion is going to be 1 part per every 10 to the 9th. Again, part. And so if you convert, again, your solute to micrograms, that's probably the most convenient for handling these parts per billion. And so next is your mole fraction. So we saw that with our gas mixtures. And so our mole fraction is just a fraction of moles of one component in the total moles. And so we just have whatever moles we're interested in, again, over your total moles, so substance A plus substance B, or whatever else was in that mixture, and we get that mole fraction. So the mole fraction has no units, but then we can just convert it to a percent, so of course just multiply it by 100, and you get mole percent. So you see those used pretty interchangeably of mole percent and mole fraction. So let's put things back to gases. And so the other thing that the stockroom does a lot in a super handy calculation is this formula. So I would write this down somewhere too on your cheat sheet or your periodic table. And so you have your concentration, your initial concentration times your initial volume is equal to your final concentration times your final volume. And sometimes you see this more specifically written like this, so M1 V1 equals M2 V2. And all that is it's more specific for molarity, but as you're seeing, it doesn't matter. So the concentration can be any unit. It's just often you see this formula and not the more general one. And so like I mentioned, you start with a stock solution, so you buy your stock solution, and then the stockroom has to do a dilution and prepare your solutions for lab. And so to make solutions of lower concentrations, more solvent is added, so the amount of solute doesn't change, just the volume. And so the concentrations and volume of the stock and new solutions are inversely proportional. So let's look at some example. And so this would be, we want to prepare 3 liters of a 0.5 molar calcium chloride solution from a 10 molar stock solution. So then the question is, if we want this much for our final, right, how much of our initial volume do we need? And so before we can figure out how much to pour in here and make our proper dilution, let's set up our calculation. So C1V1 equals C2V2. So these are our 2 conditions. So we want a 0.5 molar concentration. We want 3 liters. And so again, notice the units don't matter as long as you're consistent. So if I'm in molarity and liters, that means on my other side, I need to use molarity and liters. So you could use like milliliters, right? We could use molality. Doesn't matter. And so now we need to solve for X. And I did not fire up my calculator. So 0.5 times 3 divided by 10. So that gives us 0.15 liters, or 150 milliliters. And so now that's all that's going on in this little depiction here. So again, to properly make our solution, you start with the correct volume of your stock solution. So you measure that out precisely, pour that in, and then you dilute it. So you'd probably want to take it to around the 3/4 mark first, shake it up, make sure it's homogeneous, and then drop by drop, bring it up to your appropriate line there. All right, let's try our practice problem. To what volume should you dilute 0.2 liters of a 15 molar sodium hydroxide solution to obtain a 3 molar solution? So hopefully you set up something like this. So C1V1, C2V2, and so we had our initial conditions and units were fine. So liters, molarity, molarity. So then plug that in. So what do we get for X? 1 molar, or 1 liter. So 1 liter then. Any questions on this one? And so now we'll look at, again, what you saw in lab, and probably also what we're going to be seeing in a little bit as the cold weather comes in. And so what you saw in lab is you had your ice bath, and you added salt to it, and the temperature got lower. And so now what we're learning, so the freezing point of a solution is lower than the freezing point of the pure solvent. And so thinking about it at a molecular level, so again, you have all your intermolecular forces, except if you have a solute in there that's going to disrupt the packing of your solvent. And so what happens is again, it just lowers your freezing point. So here's your liquid solid line. So this is a triple point graph, so it has whatever compound we're interested in, and so solid, liquid, gas. And so if you notice, your blue line is for your pure solvent. Now our red is a solution. So again, looking at this liquid solid line, so this is your phase change here, melting to freezing. So you notice your solution is lower. And so then you can quantify it. So the change in temperature is going to be equal to your molality times Kf. And so your Kf is just your proportionality constant for freezing point depression, like we've seen before. So Kf depends on the solvent, and so you'd have to be given that or look that up. And so the units, and this is, again, where you watch those units. So it's typically given in degrees Celsius per molality, but again, just be careful in case it's given in another concentration. And so again, pure water freezes at 0 degrees Celsius, and so they're probably going to start salting as we get colder and colder, since salt disrupts that equilibrium. So the salt particles dissolve in water, but they don't easily attach to the solid ice, so again, preventing that ice from solidifying. And so when an aqueous solution containing a dissolved solid solute freezes slowly, the ice that forms does not normally contain much of the solute. So all that's saying, right, your ice is starting to at least make its structure, so you lowered it to the right temperature. And so as it's making that crystal lattice structure of ice in the solid state, it's essentially kind of kicking out whatever is dissolved in there. And so again, that's why you have to lower it to a lower temperature to get it to solidify. And so again, the temperature must be lowered sufficiently to make the water molecules slow down. And so now this is a Kf for various solvents. So if we were looking at water, like in lab, we could quantify what we did, see if our results match with what we expect with the Kf. And so let's look at this one. So what is the freezing point of a 1.7 molality aqueous ethylene glycol solution? And if it's aqueous, again, that's telling us our solvent is water. So take a minute or two, see if you can do that. So let's see what we got for this one. And so our formula is, again, just our delta T is equal to our Kf times our concentration. So our Kf, we want to look at water, since it said it was an aqueous solution, so 1.86. And then it told us the concentration, so 1.7. So then the first step, we just multiply them. So that gives us our change in temperature, and then it's freezing point depression, so it needs to be lowered. So formally we could take 0, since that's our normal freezing point, and then now subtract it, since again, freezing point depression. And so our new freezing point is then going to be -3, and I'll just round it to 2, so -3.2 degrees Celsius. So does that make sense for that one? And so the last thing I'll probably look at today is the boiling point elevation. And so now that's the opposite. So the boiling point of a solution is higher than the boiling point of a pure solvent. And so again, we have our proportionality constant, except instead of Kf, it's Kb for boiling. And so we could refer back to the same chart. So notice they have our normal freezing, our Kf, and then our Kb factor over on the right-hand side with all the normal boiling points. So let's look at this problem. So what mass of ethylene glycol must you add to 1 kilogram of water to produce a solution that boils at 105 degrees Celsius? And it gives you a little hint here. And let me get you the Kb for water. That would help. So 0.512. See if you can solve that. What steps would you take? So how do we do on this one? What should we start with?
No, you'd have to find the difference between the boiling point of the solution and the boiling point of the solvent if they gave it to us.
So you said we want to find our change in boiling point, so that's equal to KB times our molality. But then you said, okay, they gave it to us, so let's plug that in. So we want a 5-degree change in temperature. And so we're doing water, so aqueous solution, so this is a KB we're interested in. And so now let's solve for molality, so we can get that at least. So 5 divided by 0.512. So then we all get that we need a molality of 9.76. So that looks good, so 9.76 roughly. And so then it asks, well, what mass do we need though? And so molality is just moles over kilogram. So how many moles would we need to add to 1 kilogram? We have a 9.6 molality. And we could set it up so 9.6 is equal moles, 1 kilogram. We have our triangle trick if we need. Moles, molality, kilogram. So we want moles. So cover up moles, that means we need to multiply molality times kilogram. And so we just get 9.7. I guess I should have rounded it to 7. Moles of ethylene glycol. So do we get to this step? So all we did was determine moles, but they were asking for mass. And so now we need to find our mass of ethylene glycol. Someone have a mass handy? 62.068. Is that what other people got? And so then to find our mass, we just need to multiply that last two, so times our molecular weight. And so that gives you 606 grams then. So do we all get that? All right, that's probably a good stopping point. We don't have too much left, but I don't want to rush it. So Wednesday, we'll probably do a bunch of practice problems. So I have the homework up at the front, so you could grab that on your way out or now. So let's take a 10-minute break, and then we'll do our quiz. Okay, you need to do the last one, quiz 6?
The last two.
The last two, okay. I just need to run up and grab copies.
Yeah.
I'll do that now.
Yeah, that's all.
Did we get our quizzes from last week?
I have them, I'll hand them back. I don't think I did it yet.
Okay, I was making sure.
Yeah,
That we miss out.
I'm making sure too, I have too many papers. Thank you.
I always forget to turn it on for us.
Oh, and then for the extra credit, do you want us to just tell you what classes we registered for, or do you want an actual screenshot?
You could just, or just even an email that says, hey, I registered, it's fine.
All right.
Yeah, I have your quizzes here, so I'll hand them back during your quiz. I have too many papers, so I need to shed.
Yeah, not this week. I'm still working on this week, so I feel like last week's stuff was kind of fulfilling. That's kind of a lot.
Yeah.